Hello viewers, good morning. I hope you are doing well. Today I am going to discuss a very important small topic known as concept of orbital hybridization in chemistry. As you are aware, this concept is very often used to explain molecular structure. So we will discuss this in detail. The following points will be taken up for clarity. The whole topic has been divided into so many points noted here. In chemistry, the most vital aspect of study is the unraveling of molecular structure. That is, the topology of atoms. Topology means which atom is bonded to which other atom. The relative orientations in space and the directional properties of valence orbitals, which overlap to constitute the chemical bonds between atoms. As an example, we might be interested in knowing why is water molecule angular in shape with the HOH bond angle of 105 degrees, whereas in ammonia the bond angle is 107 degrees, but in methane it is 109.5 degrees. So all these concepts and many other similar concepts have been explained qualitatively on the basis of hybridization concept. Essentially speaking, orbital hybridization is a concept used to describe the mixing of atomic orbitals, AOs for short. That is to say, their angular wave functions to form new hybrid orbitals with different shapes, different energies, and different orientations of their wave function. This theory is particularly important and useful in explaining the molecular geometry and bonding in molecules. Then we will come to know who actually propounded this theory of hybridization. So let us begin. Soon after, Erwin Schrödinger in 1926 had given his epoch-making second-order differential equation H psi equal to E psi, where H is the Hamiltonian operator, E is total energy of the system, and psi is the wave function, known as the Schrödinger wave equation of quantum mechanics. Attempts were made to understand the nature of chemical bond. The first attempt was by Hitler in London in 1927. They developed the prototype model of valence bond theory, VBT, which was further improved by Slater and Pauling in the 1930s. Thus, the theory is now known as Hitler, London, Slater, Pauling, HLSP theory. The HLSP theory was built upon the G.N. Lewis model of paired electrons representing a covalent bond. In present times, the theory accepts the perfect spin pairing approximation. It assumes that all possible canonical structures with electrons paired in all possible ways contribute to the wave function of the molecule. It means to say that the overall wave function of the molecule is a superimposition of all possible canonical structures. During the course of refinement of HLSP theory, Linus Pauling introduced the orbital hybridization concept as an extension of the valence bond theory. This concept helps to explain certain molecular shapes and bond angles that cannot be explained otherwise by considering only the pure atomic orbitals participating in the bond formation. So this theory is very important, and Linus Pauling is credited with its proposition. The basic idea of hybridization. Orbital hybridization is, the basic idea is that Angular wave functions of the participating AOs are linearly combined to obtain wave functions of the hybrid orbitals of the molecule. Empirical rules of atomic orbital hybridization. Atomic orbitals participating in the hybridization phenomenon necessarily belong to the same atom, and they are of more or less similar energy. That is, their energy should not differ too much. They must be close enough. These AOs are actually called valence orbitals. The number and types of hybrid orbitals formed are determined by the number and type of atomic orbitals participating in the hybridization process. This process is essentially the redistribution of energy and orientation of electronic charge. The hybridization phenomenon should not be confused with a real physical or chemical process. It is just a concept which has been useful in certain aspects. The number of resulting hybrid orbitals is exactly the same as the number of participating pure atomic orbitals. However, their energies are a bit higher and they possess more appropriate direction property, thereby allowing for efficient overlap with the orbital of the atom with which sigma bonds are going to be formed. It may be noted that the hybrid orbitals form either sigma bond or contain unshared electron pair, but they do not form pi bond. The stronger bond formation by the hybrid orbitals than pure AOs outweighs the energy input for hybridization. Obviously, it should be energetically favored. The most common types of hybrid orbitals are S1p1 or sp, S1p2 or sp2, S1p3 or sp3, and so on. These are formed by the mixing of s orbital and p orbital belonging to the same shell, same subshell. These types are oversimplification. When we discuss the mathematical aspect here in this video, you would find that the subscript need not be whole numbers. Instead, they could be fractional numbers as well. For example, both the CH and CF bonds in HCF3 molecule cannot be explained on the basis of S1p3 hybridization of carbon atomic orbitals. The carbon-fluorine bond formation, the electron pair would be more strongly pulled towards fluorine nucleus than in the CH bond. Therefore, the hybrid orbitals of carbon involved in the overlapping with the fluorine 2p atomic orbital are merely S0.8 p 3.2, not S1p3. Again I repeat, not S1p3, but S0.8 p 3.2, fractional numbers. However, for the sake of simplicity, we generally speak of S1p1, S1p2, S1p3, DS1p3, D2S1p3, S1p3D2, etc., etc. One more is S1p1, S1p2 plus PDA. Here is a brief description of each type. sp hybridization. In this case, one s orbital and one p orbital, they mix together, form two singular orbitals. As you know, s and p atomic orbitals are not similar. S is spherical, p is bumper shape, but on hybridization, they become equivalent. Examples of molecules showing this hybridization include ethylene, BeCl2, CO2, etc. sp2 hybridization. In this case, one s orbital of the atom and two p orbitals of the same atom, they get mixed, form three orbitals of equivalent shape and size, energy also. They are disposed in a plane at angle of 120 degree, and the resulting molecular shape is trigonal, triangular, planar. Examples include ethylene and BF3. sp3 hybridization. In this case, s atomic orbital and three lobes of the p subset of the same atom. They are mixed to form four hybrid orbitals known as sp3 hybrid orbitals. Here in this case, they are disposed tetrahedrally. This is necessary so as to keep maximum distance between the electron pairs so as to minimize the repulsion. Examples of molecules showing this hybridization include water, ammonia, ammonium, methane, etc., etc. Sometimes deviations also occur. In case of water molecule, for example, we talk of sp3 hybridization of oxygen involving 2s and 2p-AOs. Thus we get 4 hybrid AOs, orbitals, not AOs, and there are 6 electrons. So 2 of the hybrid orbitals are filled, they contain unshared electron pair, 2 are bonding, having 1 electron each. This angle in the molecule is not equal to 109, that is tetrahedral angle. It becomes 100 degree 5. Why is this? Because the lone pairs or unshared electron pairs, they lie closer to the nucleus. In order to decrease the repulsion between them, the bond has to be expanded. Naturally, the OH bonds are constricted. So, wherever unshared electron pairs are present, deviation in bond angle from tetrahedral value takes place. In ammonia, there is only one unshared electron pair, so deviation is small. Angle is 107 degree. In ammonium, there is no unshared electron pair, so angle in ammonium is the same as for methane. The concept of orbital hybridization helps explain the shapes of molecules, types of bonds formed, and the properties of chemical compounds. It is important to note that hybridization is a simplified model used to describe bonding, and it does not represent the behavior of electrons. It provides a useful framework for understanding molecular structure and bonding, but should be seen as a model rather than physical reality. Large number of examples of atomic orbital hybridization are given in almost all the course textbooks. The students are hereby advised to work out as many examples as possible. An example of sp2 plus pd hybridization is found in case of PCl5 with 2 longer PCl bonds at 180 degree and 3 smaller PCl bonds lying in a plane at an angle of 120 degree. So in this case, because all the 5 orbitals are not similar, there are 2 types. We use the concept of mixed hybridization, that is sp2 plus pd. Let us now proceed to calculate the coefficient of mixing of atomic orbitals giving hybrid orbitals. First, we take up the example of sp3 hybridization. This method is based on the valence bond approximation. Suppose we are considering the formation of 4 sp3 hybrid orbitals by combining 2s atomic orbital, 2px, 2py, and 2pz atomic orbitals. Then we can write equation 1. We get 4 hybrid orbitals designated as 5sp31, 5sp32, 5sp33, 5sp34. Now how to get the values for these? We add up the wave function for s orbital, px orbital, py orbital, and pz orbital. We added the wave function. The equation 1 clearly shows this method. In this case, pi sp3 represents the hybrid molecular orbital, whereas psi s and psi p, they represent the respective angular wave function of the atomic orbitals, and the multiplier factors a, b, c, d, etc. They are the corresponding mixing coefficients. Now how to solve it? We need to apply certain assumptions or rules. The first rule is 2s atomic orbital is spherically symmetrical, not directional, and it is equally distributed into 4 sp3 hybrid orbitals. It implies, therefore, that the sum of the squares of the corresponding mixing coefficient ai, where I equal to 1, 2, 3, 4, will be equal to unity 1. Therefore, we can write a1 square plus a2 square plus a3 square plus a4 square equal to 1. Because all are equal, we can put a1 square equal to a2 square equal to a3 square equal to a4 square equal to 1 by 4. It means a1 equal to a2 equal to a3 equal to a4 equal to 1 by under root 4 becomes 1 by 2. This is equation number 2. Next, we assume that pi sp3 first hybrid orbital is developed along the x-axis. Clearly, the contribution of the orbital's lobes lying along y-axis and z-axis will be 0. It means the coefficients c1 and d1 both become 0. Now, using these two rules, we can evaluate b1. How? See equation 3. a1 square plus b1 square plus c1 square plus d1 square equal to 1. In this case, c1 equal to d1 equal to 0. Therefore, putting the value of a1 square 1 by 4 plus b1 square equal to 1. Transposing b1 square equal to 3 by 4. b1 equal to under root 3 by 2. This is equation 3. See, we have so far evaluated a1, a2, a3, a4, c1, d1 and d1. Now we apply the second rule regarding the condition for the mutual orthogonality of the 4 hybrid orbitals. Considering phi sp31 and phi sp32 hybrid orbitals, we can write a1 a2 plus b1 b2 equal to 0 because these orbitals are orthogonal. Putting the value of a1, a2 and b1, we can evaluate b2 and b2 becomes equal to minus 1 over 2 under root 3, equation 4. Similar considerations reveal that b2 equal to b3 equal to b4 equal to 1 over under 2 under root 3. So remember, b1 is different, but b2, b3, b4 are all equal and their values are 1 over 2 under root 3. Question 5. Now we have to evaluate which coefficients C2, C3, C4, D2, D3, D4. We apply another assumption. Assuming that one of the four sp3 hybrids, say sp3 2, will lie in the XZ plane. Therefore, it will have contributions from 2s, 2px and 2pz AOs, but not from 2py AO. Hence, the coefficient C2 will be equal to 0. Accepting that this orbital is normalized, we can write A2 square plus B2 square plus C2 square plus D2 square equal to 1, in which case C2 is 0, we already told. Putting the values 1 over 4 plus 1 over 12 plus 0 plus B2 square equal to 1. Therefore, we can evaluate B2 square equal to something from which D2 equal to under root 2 by 3 equation 6. So we have evaluated A1, A2, A3, A4, C1, C2, D1, D2. Next we apply orthogonality condition between phi sp3 2 and phi sp3 3 hybrid orbitals, and likewise between the second and fourth hybrid orbitals. So we can write A2 A3 plus B2 B3 plus C2 C3 plus B2 D3 equal to 0. Remember, here C2 is 0, therefore this term will vanish. We know the values of A2 A3, we know the values of B2 B3, we know the value of D2, therefore we can determine the value of D3. Only one unknown is there in this equation, and D3 equal to minus 1 over under root 6. This is equation 7. Similarly, we can show that D3 is same as D4 and values are minus 1 over under root 6, equation 8. Applying the normalization condition for the third sp3 orbital, A3 square plus B3 square plus C3 square plus B3 square equal to 1. We know the value of A3, we know the value of B3, and we know the value of D3. Therefore, C3 can be evaluated very easily, and C3 equal to 1 over under root 2, equation 9. Again, using normalization condition for the fourth hybrid orbital, we can write A4 square plus B4 square plus C4 square plus B4 square equal to 1. Putting the values of A4, B4 and D4, we can evaluate C4 equal to minus 1 over under root 2, equation 10. Alternatively, C4 can also be evaluated by writing A3 A4 plus B3 B4 plus C3 C4 plus B3 D4, and the same value we get C4 equal to minus 1 over under root 2, equation 11. See, we have derived all the numerical values of the coefficients A1, A2, A3, A4, B1, B2, B3, B4, C1, C2, C3, C4, B1, B2, B3, B4. Now we can put these values in the equation 1. Therefore, we get equations for the four sp3 hybrid orbital wave functions as follows. Equation number 12, 13, 14 and 15. See, the contribution of 2s atomic orbital is the same for all four. The contribution of 2px is only for the first case. This much value for the first case. For other three cases, The values are different from the first one. Likewise, the contribution of Pz and Ty, we have evaluated them and put here in equation number 12, 13, 14, 15. Thus, we have evaluated the mixing coefficients and got the final equations for the orbital wave functions. Now we take up example of sp hybridization. Very simple case, because first we have discussed sp3. We have learned all the methodologies, approximations, assumptions, etc. So here for sp hybridization, the process is very simple. Let us construct the wave function for the two sp hybrid orbitals from the 2s atomic orbital and 2px atomic orbital. Say for example, beryllium as in Be2 molecule. For doing this, we first obtain linear combination of the angular wave functions of the 2s and 2px AU. For the sake of simplicity, we represent the wave functions of the 2s and 2px AU respectively by psi s and psi p, and the wave function for the two hybrid orbitals is pi sp1 and pi sp2. Thus we get equation 16. Now let us evaluate the coefficients A1, B1, A2, B2. Since the 2s AU is spherically symmetrical, non-directional, and equally distributed between the two sp hybrid orbitals, we may write A1 square plus A2 square equal to 1. Both A1, A2 being equal means A1 equal to A2 equal to 1 over under root 2, equation 17. Similarly, B1 square plus B2 square equal to 1. It means B1 equal to 1 over under root 2, B2 equal to minus 1 over under root 2. Minus sign because the px orbital is directional. One value is plus, other value is minus. Alternatively, since both the sp hybrid orbitals are individually normalized and both AOs are also individually normalized, whereas psi s and psi p are orthogonal to each other, we can write integral pi sp1 square dx equal to integral a1 psi s plus b1 psi p whole square dx. On expansion, we get b1 square equal to 1 over 2, b1 equal to 1 over under root 2. Since both the pi sp1 and pi sp2 are mutually orthogonal, we took the values of a1, b1, a2, when we get b2 equal to minus 1 over under root 2. Because we have evaluated all the four coefficients a1, a2, b1, b2, we can now write the equation for sp hybrid orbital wave functions as equation 19 and 20. Let us now take up the example of sp2 hybridization. For example, in BF3, the linear equation for the three hybrid orbitals are written as equation number 21, showing the contributions of s orbital, px orbital, and py orbital. We have ignored pz. Applying the first assumption, a1 square plus a2 square plus a3 square equal to 1, it means a1 equal to a2 equal to a3 equal to 1 over under root 3. Likewise, second assumption, a1 square plus b1 square plus c1 square equal to 1. Considering the first hybrid orbital is developing along x coordinate, c1 becomes 0. Therefore, we can evaluate b1 because we know the value of a1. b1 equal to under root 2 by 3. Now apply the orthogonality condition. A1, A2 plus B1, B2 plus C1 C2 equal to 0, and we know C1 is 0. We know the value of A1, A2, B1. Therefore, we can evaluate the other one, B2, we can evaluate. Likewise, we can write A1, A3, B1, B3, C1, C3 equal to 0. Again, C1 is 0. B1 we already know. A1 we know. A3 we know. It means we can now evaluate B3. So B2 equal to minus 1 over under root 6, and the same value is for B3. Considering the normalized sp2 second hybrid orbital, we can write A2 square plus B2 square plus C2 square equal to 1. We know the values of A2 and B2, therefore we can evaluate C2 equal to plus 1 over under root 2 and minus 1 over under root 2. Again, the orbital Py is directional, therefore positive and negative values both are possible. Exactly in the same manner, we can show C3 is same as C2. Now we can write the wave functions for the three hybrid orbitals as equation 28, showing the contribution of each atomic orbital for the three hybrid orbitals. Now we discuss a little bit about the energetics of hybridization process. The following line diagram 1A and 1B, figure 1, illustrates that for an atom having filled 1s and 2s atomic orbital but vacant 2p atomic orbital, excitation of an electron from 2s atomic orbital to 2p atomic orbital is an energy intensive process leading to half filled 2s and 2p explode. But these two would form different bonds with say F atoms. The fact that these form similar bonds disposed at an angle of 180 degrees, it suggests their mixing before bond formation. That is hybridization, also known as energy intensive process of energy distribution, redistribution. The energy released in the formation of two sigma bonds offsets the energy input steps. If no hybridization took place, lesser amount of energy would be released. This is shown in figure 2. This is shown in figure 1b. Another diagram, figure 2, illustrates the energetics of sp3 hybridization as in case of methane. See figure 1 clearly explains that the process of hybridization leads to more stable molecule formation than without hybridization. Figure 2 explains the methodology of sp3 hybrid orbital formation. Here figure 3 in the pictorial sketch of sp hybrid orbital. Figure 4 and 5, they represent sp2 and sp3 hybridization. Given here are some simple questions with short answers. So friends, the topic of hybridization is very, very important. Although it is very elementary one, we are reading this topic right from our school days. Here a little bit mathematical part has been added, but that is necessary to know. You should remember this much. SP, SP2, SP3, these are oversimplifications. In every case, the integers should not be used. This video, however, explains the methodology, and we might have grasped a little bit I suggest please make 2-3 readings with pen and pencil and paper in your hand, then you will be able to understand what this concept is all about. The questions given over here, they are just very, very short questions, and the answers are not in detail, only hints are made, but still I think this will be useful for you. Thank you very much.